Hi, in this video we are going to solve this problem. It is a GATE 2016 and for the 2 marks problem it is in the set 2. Okay. So while coming to this problem, he is given an op-amp has a finite gain, open loop voltage gain of 100. Its input offset voltage is plus 5 millivolts. Is modeled as shown in the circuit below. The amplifier is ideal in all other aspects. So here the input voltage is given is 25 millivolts. So in this op-amp, here the input voltage is 25 millivolts and the input offset voltage is 5 millivolts. So while coming to the input offset voltage, that is VIOS. Input offset voltage means if I take an op-amp like this, okay, so if the input is not connected to both the V1 and V2, okay, let's take it as a V0. So if V1 is equal to 0 and V2 is equal to 0, then my V0 must is equal to 0. Okay, why? Because the output voltage of this op amp can be taken as a V0 is equal to open loop gain into V2 minus V1. Okay, it is a formula or expression for the output voltage of an op amp. So if my both input voltages are 0 0, then here V0 must becomes equal to 0. Okay, but while coming to the real case, in the real situation, if both my input voltages are 0, then I will not get V0 as a 0. Okay, why? Because it's due to the some internal reasons inside the operational amplifier. Okay, so to make this one as a 0, instead of giving the one of the input, okay, to any one of the input, I have to give some input voltage. This input voltage is nothing but a input offset voltage. Okay, this input voltage makes the V0 as a 0 if V1 and V2 is not connected to any other voltages. Okay, so input offset voltage can be taken as a, it is a voltage that is connected as an input to the operational amplifier to get V0 as a 0 volts if both the V1 and V2 are 0 volts. Okay, so that is regarding the input offset voltage. And given the open loop voltage gain is 100. Okay, that means its open loop voltage gain is 100. That means AOL can be taken as a 100. Okay. So here, generally in the operational amplifiers, we are going to listen that virtual ground concept. Okay. So virtual ground concept means whatever the voltage is there at the non-inverting terminal, the same voltage is going to be maintained for the inverting terminal also. That means here total it is a 25 and it is a 5 means this total voltage is 30 volts, sorry, 30 millivolts. Okay, 25 plus 5 that becomes equal to 30 millivolts is the total supply to the non-inverting terminal. Okay, then we are expecting that here also I will be having the 30 millivolts due to the virtual ground concept. It's fine, but virtual ground concept applies to the operation amplifier, that is especially ideal operational amplifier. Okay, what I mean is that if the open loop gain of an operational amplifier is infinity, nothing but it's an ideal operational amplifier, right? So if AOL is equal to infinity, then only you can apply the virtual ground concept here. That means if here the 30 millivolts is there, then here also 30 millivolts will be maintained. But according to the question, he clearly mentioned that open loop voltage gain of the operational amplifier is 100. Okay, it's not an infinity, it's an 100. Okay, so while coming to the open loop voltage gain, he is not telling about it's an ideal op amp. He's telling that it's a practical op amp with the open loop voltage gain AO is equal to 100. Okay, so one thing you have to mind that for if the open loop voltage gain is mentioned, then you should not take the virtual ground concept. Clear? If in the problem he did not tell about the open loop voltage gain, then only you can able to apply the virtual ground concept. Okay. That means whatever the voltage is there at the non-inverting terminal, the same voltage is going to maintain at the inverting terminal. But in this problem, he clearly mentioned that AOL is equal to 100. That means the virtual ground concept doesn't work out here. So now let's take here the voltage is VA and here the voltage is VB. Okay. So now according to the problem, given question, VB is equal to 30 millivolts, right? And VA is the voltage at inverting terminal. Okay, so here VA is a voltage at inverting terminal. So now, as I said that the output voltage expression for an open loop operational amplifier VO is equal to AOL into V2 minus V1. Okay, so now we'll see that I'm writing here output voltage of a open loop. Okay, Opamp. Let's take it as a minus and it is a plus. Okay, so here minus. Okay, the inverting terminal VA is there, VA, and to the non-inverting terminal VB. Okay, so now the expression for the open loop Opamp output voltage is V0 is equal to AOL into VB minus VA. Okay, that means I am just considering only this part. Clear? So now that is equal to open loop voltage gain is already mentioned, that is the 100. So I'm taking 100 and VB. VB is the voltage at the non-inverting terminal. So combinedly it is a 25 millivolts. So both these two are in series. That's why here I can take the VB as a 30 millivolts minus VA. Okay, so it is a output voltage. Okay, let's take it is the equation number 1. Clear? And if you observe this path here, if you observe here, let's take here the current I is coming from this path. Okay, and this current I is the same amount of current is also flowing through the 15 kilo ohms. Why? Because here while coming to the op amp, he said that in amplifier is ideal in all other aspects. Okay, that means whatever the current flowing to this non-inverting inverting terminal, I can take this current as a 0 due to the huge input impedance of this operational amplifier. Now if the current I is flowing through the 1 kilo ohms, the same amount of current is also flows through the 15 kilo ohms. So the expression to this one I can write that see I is equal to, here 0 volts is maintained and here VA volts I considered. So now I can take that I is equal to 0 minus VA divided by 1K is equal to, okay, that is the current flowing through this 1 kilo ohm. And similarly the current flowing through this 15 kilo ohms can be taken as here VA is there and here V0 is there. So VA minus V0 divided by 15K. VA minus V0 divided by 15K. Okay, so if I solve this one, what I will get is that minus 15 VA is equal to VA minus V0. That implies V0 is equal to 16 VA. So from this one, I can take VA is equal to V0 by 16. So let's take it as a equation number 2. Now I am substituting equation 2 in 1. Okay, see it is the equation number 1. I am substituting VA, that is V0 by 16 into this part. Now my expression for V0 can be taken as V0 is equal to 100 into 30 milli minus V0 by 60. If I simplify, 100 into 30 milli becomes 3 minus VB into 100 by 60. Clear? So later on, sorry, it is V0, right? V0. Okay, because V0 by 16, V0 by 16. Okay, V0 by 16, and that implies if I bring this V0 to the RHS side, so V0 1 plus 100 by 16, that becomes equal to 3. Okay, so if I simplify this expression, then my V0 becomes equal to 413.79 millivolts. Okay, so solve out this one, you will get the 413.79 millivolts. So it is the output voltage of the given circuit. So he is asked the output voltage in millivolts. So here the answer is 413.79. Okay, here already millivolts expressed, so you need not to mention here millivolts. Okay, so it is a way of solving such type of problems. So the one thing you have to mind is that if the open loop voltage gain he mentioned some figure, then don't apply the virtual ground concept. Okay, if he is not discussed or mentioned anything about the open loop voltage gains, then you can take that open loop voltage gain can be infinity. Now you can directly apply the virtual ground concept. Okay, so it is a way of solving such type of problems. So please subscribe my channel, share, like and comment. Thank you.